Good morning, everyone. The title of my thesis is Studies on Above Ground Storage Tanks Subjected to Seismic Excitation and Foundation Settlement. However, in today's talk, we'll focus primarily on foundation settlement because of time limitation. The outline of today's talk is as follows. I'll start with a brief overview about the tank structure and their failure. Then I'll talk about settlement measurement and the Fourier transformation, following which I'll introduce the APS 653 method which is currently being used, and then I'll talk about the primary investigation that we conducted. Then I'll propose the alternate method which we suggest and will validate and compare the method with the existing API 653 method. Lastly, I'll conclude the work we did in this study. This is how a typical API 650 tank looks like. These tanks are generally used to store a variety of products such as water, petroleum, chemicals, etc. These tanks are very economical because the diameter thickness ratio roughly ranges between 1000 to 7000, which means that you can store a huge amount of product using very little amount of material. However, such a small thickness makes these tanks prone to buckling failures, especially under horizontal loads such as seismic and wind loads. Moreover, these tanks are built on soft foundation, which makes them prone to differential settlement. There are two kinds of differential settlements which we typically look. One is global settlement, one is local settlement. I'll talk in more details in upcoming slides. This is one of the failure which took place because of differential settlement. You can see oil spill all across the tank farm and how much damage it caused. Now let's look into a typical tank structure and its major components. A tank has a tank bottom, a tank shell, and a wind girder. These type of tanks are called open top tanks. The counterpart is a closed roof tank. The closed roof can be using a conical roof, spherical roof, or elliptical roof. Open top tanks are more common in industry, and therefore the focus of our study is going to be on open top tanks. Now let's look into how settlement is measured for a tank. Typically, the settlement is measured around the tank circumference. Each of the small circles represents a measuring point. The central circumferential angle theta is used to keep a track of these points. We can plot the settlement on an XY plot using the central circumferential angle, as I'll show in the next slide. Here's a sample profile, and on the x-axis you can see the central circumferential angle, and on the y-axis you can see the settlement measured at that particular angle. Each of the squares represents a measuring point. We can convert the discrete data points into continuous series using Fourier transformation as shown in the equation, where Z average is basically the average or the uniform settlement. En and Bn are Fourier coefficients. The equation can be further simplified into a single harmonic with phase shift as shown. Let me give you an example. If we do the Fourier transformation on sample profile, what are different components look like? This is what we get for cos theta component. On the x-axis we have the central circumferential angle, on the y-axis we have the settlement amplitude. Similarly for cos 2 theta, cos 3 theta, and cos 4 theta. When I combine all these four components along with the average, let me show you how the profile looks like. We can see the combined profile is almost a perfect match as the data points. The R-square value of this fit is 0.99. Now you would wonder whether all profiles exhibit such a behavior. No, the profiles which exhibit such behavior are called global set of profiles, and the counterpart is local settlement profiles. The way we define global settlement profiles are the one which have an R-square value of greater than 0.9 with Fourier component less than n equal to 4. A local settlement profile would look like this, where you have a single dip or multiple dips like this. These dips cannot be represented using Fourier coefficient less than n equal to 4. Therefore, the focus of our study is going to be only on a global set of settlement profiles, which are more common. Let's look into the existing method using API 653 to evaluate the differential settlement. You plot the settlement as shown before in XY plot, then you fit a best cosine fit, and then you measure the difference between the cosine and the measured settlement values, which is called UI. The differential settlement is basically the difference between the neighboring UI values as shown. The maximum allowable differential settlement is capped using the following equation by the code. This equation was proposed by Marr and co-workers in 1982, where L is the distance between two measuring points, Y is the yield strength of the material, H is the height of the tank, E is the modulus of elasticity. The coefficient of 2 was initially not there, but code added it as a factor of safety. About the limitations of this method. First, it's based on beam theory rather than shell theory, which is more applicable to tank structures. Mars simplified the assumptions of beam theory and applied it to shell structures when he proposed the method. Second, even after the factor of safety, the material at failure goes beyond yield stress and has a yield strain of 0.007. Third, it does not differentiate between different harmonic components. There's a single value which caps the maximum settlement. Fourth, the method can only be applied if the R square value with a single cosine fit is greater than 0.9. The point 3 is something which we wanted to question because the rest of them are very clear. We are not sure whether the differentiation of higher order harmonics is required or not. So that's where our primary investigation began. We looked into 4 different tank models. All the tank had a height of 40 feet and we changed the diameter. The first tank model had a diameter of 40 feet and aspect ratio of 1, the second with a diameter of 60, third with a diameter of 100, and fourth with a diameter of 160. This is a broad range of tanks which are typically used in the industry. We did finite element modeling using Abaqus FEA software. The material model used were A36 for the wind girder and A516 grade 70 for tank shell, which are typically used in the industry. The nonlinear material properties were modeled in Abaqus. This is a stress strain curve for both the models. We used screw stress strain behavior based on ASME equations. The element used is S4R element. It's a typical shell element with 4 nodes and reduced integration. We had a finer mesh near the wind girder and shell junction where the maximum stresses occurred. This is how a typical mesh looked like for a given model. You can see near the wind girder and the shell junction, as discussed before, we have a finer mesh. In the first step of the analysis, we applied the gravity load and the boundary condition was spin all around the bottom. In the second step, we did the Rix analysis with nonlinear geometry on, and the boundary conditions were such that it spin in plane direction, and in the vertical direction we applied the harmonic settlement. We wanted to investigate the difference effect of different harmonic components, so we went on applying harmonic profiles such as cos theta, cos 2 theta, cos 3 theta until we get the strain values of 0.007 in the tank structure. In this slide, what we see is on the x-axis different tank models and different harmonic wave numbers. On the y-axis, we see the normalized settlement values which we got from finite element analysis corresponding to maximum strain of 0.007 in the tank structure. The normalization is done based on the value which we got for harmonic component n equal to 2. So the component n equal to 2 will have a value of 1. Based on this plot, we can clearly see the difference between the limiting values for different harmonic components. There's a huge change between n equal to 2 limiting value compared to n equal to 3 and n equal to 4, irrespective of what tank model we are looking at. Therefore, it's important that we consider the differentiation between the effect of different harmonic components. This is a result for model 2 with cos 4 theta component from a primary investigation. You can see the maximum magnitude of displacement taking place near the wind girder and shell junction. Now the question is, what should we do given all these limitations? Then we came up with the idea that why not we come up with a new method which takes care of all these limitations and is able to capture better the behavior of tank structures. After doing a lot of analysis and discussion, we came up with this method which we call as cumulative damage factor. In this method, the C2, C3, C4 are nothing but the Fourier coefficients which I showed you before. Emax is the maximum error between the Fourier fit and the actual settlement values. S is the settlement value which was proposed by Marr. U2, U3 and U4 are limiting values for each of these components. What the method does is it calculates the damage because of a single component and then adds them up and cumulatively calculates the entire damage to the tank structure. Therefore, cumulative damage factor. The cumulative damage factor, if it's less than 1, the tank structure is good and fit for use. If the tank structure has a cumulative damage factor of greater than 1, it means the tank is not fit for use. Now the last question is, how do you evaluate these limiting values or the U star values for different harmonic component? But before we do that, let's first define what limiting values are. The way we define limiting values is by capping the maximum membrane stress in the tank shell to the yield stress level. This will ensure that material does not go beyond yielding or, or buckling. In order to find a trend for limiting values for different tank geometries, we did numerous finite element analysis. On the x-axis we have the tank diameter, on the y-axis we have the tank height. Each circle on this graph represents a tank model which we analyzed in Abaqus for limiting settlement values for different harmonic components n equal to 2, 3 and 4. Based on those analysis, after looking at multiple geometric parameters and doing regression analysis, we finally came up with the equation which represents the trend for limiting settlement values. We found that the limiting settlement value is a power function of the geometric ratio, which is defined as d square over h. In this graph, on the x-axis we have d square over h, and on the y-axis we have limiting settlement values. Each solid circle represents a limiting value which we got from finite element analysis, and the solid black line represents the best fit curve based on the regression analysis. The R-square value of this curve was also found to be 0.99. Before we go any further, let's try to understand where this geometric ratio came from. This is the equation which is currently being used by the code. We can rewrite the equation by separating the material component and the geometric component, where L is nothing but the distance between two measuring points, which can be substituted as the perimeter divided by the number of measuring points. Upon making that substitution and simplify the equation looks very similar to what we obtained from our analysis. D square over h is the geometric ratio multiplied by a coefficient. However, the key difference is that this coefficient keeps changing for each harmonic component and is not same for all the components, and so does the power for d square over h, or the geometric ratio. Now let's talk about validation of this method. To validate this method, we used actual settlement data and did finite element analysis and compared the results with the proposed method. This is one of the sample profiles which we used in the finite element analysis. Before I go further, let me introduce this concept of settlement amplitude, which is nothing but basically scaling a settlement profile. It's not necessary that the input value of the settlement magnitude would result in tank to yield. We might have to scale up the profile so that the tank model goes and yields. Let me give you an example. This is sine theta where the settlement amplitude is 1, and if we scale it up by a factor of 2, this is how the profile would look like. Similarly, when we do this for the actual settlement profiles or the measured data which we have, we can compute the so-called failure settlement amplitude, which is basically the amplification factor at which the settlement would cause tank to yield. Based on the finite element analysis, we obtain the value of failure settlement amplitude and failure settlement profile. For those corresponding values, we calculate the cumulative damage factor, and if the cumulative damage factor at the failure settlement profile turns out to be greater than 1, it means the proposed method indicates the tank has failed, as well as the finite element analysis says the tank has failed. Let's look into different tank models which are used for the validation. The first set of tank model contains tank with a constant height of 40 feet and different tank diameters. The second set contains tanks with a constant aspect ratio but different tank heights and tank diameters. The third set contains tanks which were created using random functions. The tank height, tank diameter, specific gravity, as well as the design wind speed were randomly selected before designing these tanks. This was done to have a complete blind test. In this graph, the results for validation for set 3 tank models are shown. On the x-axis, we have different tank models. On the y-axis, we have the cumulative damage factor evaluated at the failure settlement amplitude suggested by the finite element analysis results. Clearly, irrespective of the settlement profile or the tank model, we always get a CDF value of greater than 1, which validates the proposed method. Now let's talk about comparison of the proposed method with the API 653 method. Just like we calculate the failure settlement amplitude based on finite element analysis, we can do the same for the proposed method and the API 653 method. Having done that, we now normalize these values with the failure settlement amplitude which we got from finite element analysis. In this figure, we have the results for normalized settlement amplitude for profile 3 for say 3 tank models. On the x-axis we have different tank models. On the y-axis we have normalized settlement amplitude. If the normalized settlement amplitude is greater than 1, it means that the method estimates a higher allowable settlement value compared to what we would get from finite element analysis. Therefore, the method is not good. However, if the value is less than 1, it means the method gives conservative value and is good to be used. As you can see, for both of the methods, API 653 and the proposed method, we get conservative results for profile 3. However, API 653 gives way too conservative results for few of the tank models, as low as only 20% of the capacity. In this particular figure, we see the results for profile 2. Again, on the x-axis we have the different tank models, on the y-axis we have the normalized settlement amplitude. Here we see a drastic change compared to profile 3, which we saw in the previous slide. The API 653 gives way too unconservative results, especially for tank 106, where we get a settlement amplitude as close as 2. Let me summarize what we have learned so far. The first thing we understood is that global set of settlement profiles can be transformed into different harmonic components using Fourier series. The second thing we learned from our primary investigation was that different harmonic components have different limiting values. Therefore, the differentiation between them is important. The third thing we learned was that the current code provision do not have a provision to differentiate between the effect of different harmonic component. There's a single value which captures or limits the allowable settlement. And the fourth thing we learned from our finite limit analysis is that the current method leads to either way conservative results or non-conservative results depending on the settlement profile, and therefore it's not accurate. Let me summarize what we have done so far in this particular study. First and foremost thing which we understood is that the settlement can be transformed into Fourier component using Fourier transformation. Second, that each of these components have a different limiting values based on our preliminary study. Third, the existing method in API 653 does not capture this difference. And finally, this has led to unconservative results for few of the profiles and overly conservative results for few other profiles. Let me show you how the proposed method get past all the limitations that we showed for the API 653 method. The first limitation was that it's based on beam theory rather than shell theory. The proposed method is based on finite element analysis, which has its formulation based on shell theory because we're using shell elements. Second, the existing method allows material to go beyond yielding to a strain level of 0.007. The proposed method is based on limiting the maximum stress to yield level, therefore there's no question on going beyond yielding. Third, it does not differentiate between the effects of high order harmonics. The proposed method captures the difference between different harmonic components and individually calculates the damage and then cumulatively calculates the complete damage. And therefore it leads to more accurate and conservative results as we found from finite element analysis. Thank you for your time. Please let me know if you have any questions.